All right. In the last video, we talked about how to model this aircraft. So, again, our goal is to model as close to the aircraft as possible. As you can see here, it is close, but um, there are a few things that we can tweak. We can keep tweaking until we get it right. But the wings and fuselage and tails are pretty close. The the pods may be a little bit longer, but I'm actually going to hide the pods because it's not gonna be an important it's not gonna be important to the analysis, at least in the confines of what we are going to do. It'll be nice for you to see the performance without the interferences of the pods. All right. So the pods are there just to hold the lifting fans. It doesn't really add that much of an aerodynamic benefit. Um, but this is our actual aircraft. Again, looks pretty close to how the Alia looks like. All right, so now we want to find how this performs, right? That's the whole point. Like we want to identify the performance, of this aircraft, so that you can modify it however way we want to improve the performance, right? At least that's one of the challenges. So um, now we're going to perform an aerodynamic analysis, which means we're going to measure lift, or we're going to estimate lift, drag, all of that stuff. All right. So in order to do that, let's go to analysis and then go to Aero. So there is a app called VSP Aero. Go ahead and click it. So that should open up this console right here. So I'm going to minimize this. All right, it's going to open up this console. Now, what this is, there's a lot of buttons here, which we'll walk through it. It should be pretty straightforward. But we'll go through one by one. Um, First things first, we need to save, right? OpenVSP can actually crash. Um, and if it crashes, there's no autosave option. You have to start from scratch. So uh, it's uh, it's always good to save. So let's click save. Put it in a folder that you know. So I'm gonna do Air Masters. All right. So I'm gonna do. I already have a file named Alia, but I'm gonna name it as um, Alia, Alia demo. Okay. So now I have the file saved. All right. We don't need to change much on this. All of this will automatic like self-populate. The only thing we need to set is the angle of attack. So I want to go from like 0 degrees to about say maybe about 20 degrees in increments of 20 points. All right. So that's like, I hope you know what angle of attack is. Um, just a orientation of the aircraft relative to the wind. So we want to estimate how the lift and drag changes the function of angle of attack. All right. Now the reference area and lengths, because we modeled it close to the actual dimensions of the aircraft. So let's go and click model. And the reference length should be the mean aerodynamic chord. This is the average chord, but mean aerodynamic chord is usually the best reference for an aircraft. So yeah, let's click that. We don't need to change anything else. Our reference wing is the main wing. Uh, yeah, we don't necessarily need to do any of this. You can if you want to change anything, just add, just change the number of wake iterations to like 4. So the more number of these iterations and nodes you have, the more accurate the results will be, but also it'll take a lot of time to compute. All right. So that's it. The only thing we changed is going increasing angle of attack 0 to 20 in 20 points. That means we are simulating every angle of attack from 0 to 20. Improved the default from 3 to 4, I think, right? The number of iterations. That's pretty much it. Nothing else need to be done. Oh, another thing, let's claim symmetry because there's no use in running the analysis for the entire aircraft because our aircraft is symmetric. So let's claim symmetry so that the simulation only runs for half the aircraft and then pretty much mirrors the other half. All right. So make sure to click on XZ symmetry, increase the number of nodes, etc. Yeah. Move, select the reference area and length from the model through mean aerodynamic code. All right. Once you do that, just prepare solver. So as you can see, that's the half of the aircraft being modeled. And then let's launch the solver. So it'll go through and do calculations for every angle of attack. And as you can see, it's going through and running it. Now, depending on the number of number of iterations and nodes you have, it's your results, your computational time may be different. Okay, so here's the resultant variation. Here's the results manager, but where you can actually see the variation of different parameters. All right, what you're seeing is the distribution of lift across the main wing and the tail. But what we want is the sweep. Let's go to sweep, and let's go to on x-axis have angle of attack. Remember, this is the angle of attack variation from 0 to 20. And then the y-axis, we have the CL total, right? So we know exactly at about 10 degrees, we are creating lift about 1.1, which is great. So then we can go to drag. We can do CD total. That's our drag data. And we can also plot, like, if we want efficiency, this is the efficiency. L over D is lift over drag. How is, that tells you, how much lift is being produced on the aircraft when compared to the drag. The higher the number, the more efficient the aircraft will be. All right. Now, when you go back and change the airfoils, this will actually change. All right. So look at that, right? We're getting up to, I mean, this is an ideal scenario. Sometimes it can be really hard to get an L over D of 30. But like we have a high aspect ratio wing, so it's not completely impossible, but this is also in an ideal scenario. We don't know what airfoil is being actually used on the aircraft. So that's where we can get some creative freedom to use different airfoils to see, if we can improve the baseline performance. So, uh, yeah, that's great. There are a lot more parameters here, so you can educate yourself on what all of these terms mean. But in terms of efficiency, this is what we care about: lift over drag. So another thing that we can do, I'm sure you are familiar with stall, right? So stall is once beyond a certain angle of attack, the airplane will not be able to produce lift, and then it stalls. But as you can see in here, right, the lift continues to increase even after about 20 degrees, right? Now this is not realistic because in real world, the flow separates from the airfoil and then you stall. But the default simulation settings doesn't account for stall. This is all from a pure inviscid or zero viscosity assumption, where we are not modeling this flow separation on the wing. However, there's a subroutine in the analysis where we can, go to the advanced tab, select the stall model from being off to on. That's the only thing we need to change, right? And then, we can launch the solver again. So I'm going to close this, prepare solver. Again, only thing I change is, change the stall model from off to on. And I'm going to launch the solver again. So it's going to do the analysis again. And hopefully this time, it kind of shows the stall, in the results. So let's wait for the results manager to pop up. There it is. Yeah. So if I go to alpha and CL, there it is, right? As you can see, in the previous runs, the CL kind of kept increasing forever, right? In reality, as you know, that does not happen. So with the stall model being on, it can estimate when the stall would be based on the airfoils used in the analysis, right? So well, after about 10 degrees, you stall, right? Now, how that changes the L over D, Like, look at that, right? It's a bit different. So previously, I think we were getting about 35 or something, but now, it reduced a little bit, right? So again, um, there are ways by which you can make it a little bit more realistic. There are a lot of advanced controls that you can employ if you know what they mean. But again, just for a basic analysis, this should be more than enough. Again, the software is capable of a lot more things than we talked about, but you have the basics here, and that's kind of pretty much what we need. We don't need to go that deep into all of the different things to find differences in the performance. So if I go back to main wing, sorry, if I go to main wing and then say I want to change from NACA 0012 to a 12% thick airfoils, that's 0010 and I'm going to add 2% camber. So that's, let's say 4% camber. That's NACA oh, uh, 0 0.0. Let's do 2%, right? Um, 212, but I'm going to move the camber location to 0.4, so that'll be a NACA 2412. All right, so that is the now I changed the airfoil from 0010 to 2412. All right, so that is for my main wing in section. I think let's go back. So if your model, let me go back. If your model disappears, don't worry, it's still there. It's just being hidden. So go select this, select all of these, and then click show. You'll get your aircraft, right? So the model disappears after an analysis. It doesn't mean it's deleted. It's not being shown. Okay. So now I changed the airfoil, right? It looks a little bit thicker, right? And the inboard. So now so that's 2412. Um, I'm gonna change the outbound, like the section two to say maybe a 2212, right? Again, this is where you can, you know, have a creative freedom to pretty much change whatever you want to change. Ooh, no, 02. Okay, the 212. All right. So let's see how this behaves. So now we have changed the airfoil on our main wing. Let's go back and do the analysis again. Everything stays the same. Just close this out. Let's prepare the solver, launch the solver. I let it run through. Let's wait for the results manager to show up. All right, let's go to sweep. Uh, X, I want angle of attack, and Y, I want the CL total. Right, look there, right? Now I think we had stall around like greater than 10 degrees. The stall is a little bit reduced, and then I go to lower D. Uh, yeah, I mean we didn't take too much of a hit, but I think the angle is a slightly smaller than what we had before. But again, this is where you get to play around with the different airfoils to see if it makes a difference in the performance. Right. But again, you can also add winglets. You can do a lot of different things, that, to the main wing. Let's see, CD total, there's there, right? There's a lot of things you can do to, yeah, to see if you can make a difference. All right. So yeah, that is the analysis, the aerodynamic analysis of the Alia aircraft. Um, feel free to play around with it, and I hopefully we'll see some interesting design, interesting variations and ideas in the competition. All right, thank you.